Hello everyone, and welcome to our training series on manufacturing lithium-ion batteries. Today, we are diving into Chapter 3, Lithium-Ion Battery Cell Structures and Cell Types. In this session, we will categorize batteries in two important ways. First, we will look at their physical form factors, such as cylindrical and prismatic shapes. Second, we will discuss the different cathode active materials used in them, focusing on common types such as NMC. We won't get bogged down in deep chemical formulas in this video. Please refer to your reading materials for those technical specifications. Instead, our goal today is to help you identify these different cell structures and chemistries as they appear on the production line. Let's get started. Learning objectives. Here, we outline the primary goal of this chapter: to provide you with a clear understanding of the components and configurations that make up a lithium-ion battery. To appreciate the technology you will be manufacturing, it helps to look briefly at its origins. The photo on the right features three giants of our industry: Akira Yoshino, John Goodenough, and Stanley Whittingham. They were awarded the 2019 Nobel Prize in Chemistry for their contributions to the development of the lithium-ion battery. I have listed their key milestones here to highlight how the components evolved over time. We went from Whittingham's early titanium disulfide cathode in the 70s, to Goodenough's lithium cobalt oxide, and finally to Yoshino's use of carbon-based anodes in the late 80s. This history is important because it shows that the materials inside it define a battery. As we move forward, we will look at the modern versions of these cathodes and anodes that you will be handling on the production line. For a more detailed background, please refer to Chapter 3 in your training book. Terminology. Before we get into the technical details, I want to pause on this list of terminology. As you begin your work in battery manufacturing, you will encounter a lot of specialized vocabulary, terms like intercalation, specific energy, and specific power. I won't define every single one of these for you right now, but I do want to give you some advice: treat these terms as the foundation of your new trade. Make sure you take the time to read the definitions in your training material and understand not just what they mean, but how they are used in our daily operations. I specifically want to draw your attention to the list on the right side of the screen: acronyms like NMC, NCA, and LFP. These represent the different chemical breakdowns of cathode types. We are going to study these in detail because the cathode material effectively dictates the battery's personality and performance. So, keep these terms in mind, and let's move on to see how they apply to the actual cell structures. Cathode. Now, let's focus on one of the most critical components of the cell, the cathode. As shown on the slide, the cathode is the positive electrode. To put it simply, when a battery is discharging, powering a device, lithium ions migrate to this electrode. I want you to look at the diagram on the right. This illustrates the basic concept developed by Akira Yoshino. You can see the lithium ions traveling from the negative side, the anode, through the electrolyte and the separator, to the positive side, the cathode. This flow is what generates the electrical current. In manufacturing, the cathode is often considered the heart of the battery because it largely determines the cell's overall performance. It dictates the capacity, the voltage, the cost, and even the safety of the final product. We use different materials for different needs. For instance, lithium cobalt oxide, LCO, is great for small consumer electronics like your phone. In contrast, lithium iron phosphate, LFP, is widely used in electric vehicles because it offers excellent thermal stability, meaning it is safer under stress. There are many different cathode chemistries, and I encourage you to read the detailed breakdown in your training guide to understand the pros and cons of each. Active materials for cathode. We just discussed what a cathode is. Now, let's look at what it is made of. On this slide, you see a list of acronyms: NMC, NCA, LFP, LCO, and others. In our factory, you will hear these terms constantly. They represent the different active materials. Think of them as different recipes for the cathode paste. Why do we have so many recipes? Because each one offers a different balance of performance. Let's take a look at the chart on the right. It compares specific energy, which is essentially how much energy a battery can hold relative to its weight. You can see that NCA, lithium nickel cobalt aluminum oxide, and NMC are at the very top. This high energy density is why they are often chosen for long-range electric vehicles. Lower down the chart, you see LFP. While it holds less energy per kilogram, it is incredibly durable and safe, making it ideal for other applications. You don't need to memorize the full chemical formula for every acronym right now, but you do need to understand that the material dictates the process. I strongly recommend you review the breakdown of cathode types section in your training material to familiarize yourself with what each letter stands for. Slide 1 of 2 for active materials of cathode, NMC. Let's zoom in on one of the most dominant cathode chemistries you will see in modern manufacturing, NMC, which stands for lithium nickel manganese cobalt oxide. I want to draw your attention to the diagram on the right. This is called a radar chart or spider chart, and it is the best way to visualize a battery's personality. Each point on the hexagon represents a different characteristic, such as safety, cost, lifespan, and specific energy. The reason NMC is so popular, especially for electric vehicles, is that it covers a large area of this chart very evenly. It is an all-rounder. It provides a good balance of high energy density and decent cycle life without compromising safety too much. However, not all NMC is created equal. You will often hear numbers attached to it, like NMC 811. As the slide explains, these numbers represent the ratio of metals. NMC 811 means the cathode is 80% nickel, 10% manganese, and 10% cobalt. Changing these ratios changes the shape of that spider chart. More nickel generally gives you more energy, but it might affect stability. As we go through training, you will learn how different ratios affect the production process. For now, remember that NMC is the industry's versatile workhorse. Slide 2 of 2 for active materials of cathode, NMC. We are continuing with NMC, lithium nickel manganese cobalt oxide. This table provides a technical snapshot of what makes this chemistry so dominant. You will see specifics here regarding voltage ranges, charge rates, and thermal limits. I won't read every data point, but I want you to focus on the remarks section at the bottom, which summarizes why this matters to us. NMC is considered a hybrid cell. This means it doesn't just do one thing well, it provides both high capacity and high power. It's versatile. Because of this balance, it has become the favorite chemistry for a wide range of uses, from e-bikes and medical devices to industrial applications and, most notably, electric vehicles. Its market share is increasing because it is reliable and effective. As you work on the line, you will likely see more NMC cells than any other type, so understanding these general operating parameters, like the typical cycle life of 1000 to 2000 cycles, will help you spot quality issues if they arise. Take a moment later to review the specific voltage and thermal numbers in this table, as safety is always our priority. Active materials of cathode, NCA. Next, we move to NCA, lithium nickel cobalt aluminum oxide. If you look at the spider chart on the right, you'll notice it has a very similar profile to NMC, but with one standout feature: specific energy. You can see that the green shaded area extends farther out towards the top than almost any other chemistry we use. This high energy density makes NCA the top contender for applications where space and weight are at a premium. Still, you need maximum range or runtime, most notably, in high-performance electric vehicles. However, this performance comes with trade-offs. As you can see on the chart, safety and cost are areas we need to be careful with. The high nickel content provides great energy but requires precise manufacturing conditions to ensure stability. So, when you see NCA on the production schedule, know that you are building a high-performance cell that demands strict adherence to quality controls. Slide 1 of 2 for active materials of cathode, LFP. Now we arrive at LFP, which stands for lithium iron phosphate. Let's look at the spider chart on the right. You will immediately notice a very different shape compared to the NMC or NCA charts we just saw. While LFP has lower specific energy, meaning it doesn't hold as much charge for its weight, it excels in two critical areas, safety and lifespan. You can see that those sections of the chart are very strong. This makes LFP the ideal choice for applications where safety and durability are more important than pure range or lightweight design. That is why you see LFP batteries widely used in energy storage systems, like big grid batteries, and increasingly in short-range electric vehicles. If you are building a battery that needs to last a long time and operate safely under tough conditions, LFP is often the chemistry of choice. It offers unmatched stability, which is a key selling point for our customers. Slide 2 of 2 for active materials of cathode, LFP. We are wrapping up our look at cathodes with this technical overview of LFP. I want to focus your attention on the remarks section at the bottom, as it highlights the unique personality of this chemistry. First, LFP is known for having a very flat voltage discharge curve. This means that as the battery is used, it delivers a very steady, consistent voltage right up until it is almost empty, providing stable power delivery. Second, and perhaps most importantly for us in manufacturing, this is one of the safest Li-ion batteries available. If you look at the thermal runaway row, you will see it can withstand temperatures up to 270 degrees Celsius before becoming unstable. This high thermal limit makes it incredibly robust compared to other types. Because of its safety profile and stability, LFP is used primarily for energy storage systems, such as grid backup, and in markets where long endurance is more critical than having the lightest possible weight. Please take a moment to read through the specific voltage ranges in the table to understand how they differ from the NMC cells we discussed earlier. Slide 1 of 2 for active materials of cathode, NMC versus LFP. Now that we have looked at them individually, let's put our two biggest contenders head-to-head, NMC versus LFP. This comparison is crucial because these two chemistries effectively split the market. First, let's look at longevity and charging. LFP is the marathon runner. It has a longer cycle life, sometimes up to 10,000 cycles, and can be charged to 100% repeatedly without damaging the battery. In contrast, NMC typically prefers to operate between 80% and 90% charge for daily use to prolong its life, though it can often accept a faster charge rate. Next, consider safety and cost. As we discussed, LFP has superior safety ratings and is less susceptible to thermal runaway. It is also generally cheaper to manufacture because it doesn't require cobalt, which is an expensive and scarce material. However, NMC wins on output. Because of its higher energy density, NMC is more efficient for applications that require both light weight and power, such as consumer electronics and drones. If you look at the graphic on the right, you can see the literal difference in ingredients: nickel, manganese, and cobalt versus iron and phosphorus. Ultimately, the choice comes down to what the customer values more: raw energy density or long-term durability and safety. Slide 2 of 2 for active materials of cathode, NMC versus LFP. Here, we have a detailed breakdown of the technical trade-offs between these two dominant chemistries. I want to zoom in on two practical factors: cost and longevity. Look at the bottom row regarding costs. You will see that LFP is generally 5 to 15% cheaper over its life cycle. The main reason is raw materials. NMC relies on cobalt, which is expensive and often in short supply, whereas LFP uses abundant iron and phosphate. Now, look at the longevity section. While LFP has a longer overall lifespan, there is a specific characteristic you should be aware of: LFP batteries tend to degrade faster in the first 6 months before stabilizing. This is a known behavior that we factor into our quality metrics. In contrast, while NMC offers superior energy density, the safety row reminds us that it has a higher risk of thermal runaway. This means that when you are handling NMC cells on the line, your adherence to safety protocols is even more critical than with LFP. Please keep this table handy as a reference guide. It explains why our customers choose specific cell types for their products. Cathode active materials, LCO. Next, we have LCO, lithium cobalt oxide. This is essentially the original lithium-ion chemistry that started the mobile revolution. I want you to look at the spider chart on the right. You will see it has decent specific energy, which is why it has been the standard choice for laptops, smartphones, and digital cameras for decades. It packs a lot of energy into a very small space. However, if you look at the other axes, you will notice significant weaknesses. Safety and lifespan are quite low compared to the NMC and LFP cells we just discussed. Furthermore, the cost is high because this chemistry relies heavily on cobalt, which is expensive. Because of these limitations, especially the lower safety profile and high cost, you will rarely see LCO used in large electric vehicle batteries. However, for small, portable electronics where the battery doesn't need to last 10 years, and weight is the priority, it remains a very common active material. Cathode active materials, LMO. Next, we have LMO, lithium manganese oxide. If you look at the spider chart, you will see a balanced profile, but its standout feature is specific power. This refers to the battery's ability to deliver high current quickly on demand. Because of this ability to discharge energy rapidly, LMO is a popular choice for power tools, such as cordless drills and saws, and medical devices. It provides that sudden burst of power when needed. While it is safer and cheaper than the cobalt-based LCO we just looked at, it generally has a shorter lifespan and lower capacity. That is why, in modern manufacturing, you will typically see this chemistry used in specific high-power applications rather than for long-range electric vehicles. Cathode active materials. Finally, we arrive at LTO, lithium titanate. This chemistry is the outlier of the group. If you look at the spider chart on the right, you will see a shape that is almost the opposite of the NCA or NMC cells we saw earlier. Its specific energy is very low. This means LTO batteries are heavy and bulky for the amount of energy they store. You definitely wouldn't want this in your cell phone or a long-range car. However, look at the safety and lifespan axes, they are arguably the best in the industry. LTO is incredibly robust. It can be charged very quickly and can last for tens of thousands of cycles without degrading. Because of this unique profile, LTO is used in specific heavy-duty applications where longevity and fast charging are more important than weight, such as electric buses that need to charge rapidly at bus stops or heavy industrial equipment. Anode. Now that we have covered the cathode, let's flip to the other side of the battery, the anode. As shown in the diagram on the right, the anode is the negative electrode. Its job during discharge, when the battery is powering a device, is to release lithium ions and electrons to flow to the cathode. While we have many options for cathode materials, such as NMC and LFP, the anode world is much more standardized. The material you will encounter most often is graphite. Why graphite? It is chosen because it is conductive, durable, and has a specific crystalline structure that is perfect for intercalation, holding those lithium ions like a sponge. On the production floor, you might handle two types: synthetic graphite, which offers higher purity and better performance. Natural graphite is generally more cost-effective. Just as the cathode, the anode plays a major role in the battery's safety and life cycle. It needs to be highly porous to absorb electrolyte and highly conductive to move energy efficiently. Take a moment to look at the diagram to visualize the flow of ions versus electrons, as understanding this loop is key to understanding how the cell functions. Anode, active materials. We just established that graphite is the standard, but as our industry evolves, we are exploring new materials to further push performance. This slide lists some of the advanced options you might encounter. The most exciting development right now is silicon. If you look at the diagram on the right, you can see a comparison between a conventional carbon-based anode and a new silicon-based structure. The key difference is capacity. Theoretically, silicon can hold 10 times more energy than graphite. However, there is a catch. When silicon absorbs lithium ions, it swells up significantly. Imagine a sponge expanding until it cracks. This volume expansion can physically damage the battery structure over time. So, while materials like silicon, MZenes, T3C2, and SiO2 offer incredible potential for higher capacity and faster charging, they often come with engineering challenges we are still working to solve. For now, just be aware that while graphite is our bread and butter, these materials represent the future of high-performance cells. Electrode thickness. Now that we know what materials we are using, let's talk about how we apply them. I want you to look at the image on the right. This is a microscopic cross-section of a battery. Think of it like looking at the layers of a sandwich from the side. You can clearly see the layers of cathode, separator, and anode stacked together. In our manufacturing process, the thickness of these electrode coatings is incredibly precise. We typically operate between 50 and 100 micrometers, with 70 micrometers being a very common standard. To give you a sense of scale, that is roughly the width of a single human hair. Why do we care so much about this specific thickness? It comes down to a trade-off between capacity and power. If we make the layers thicker, we pack in more active material, which gives us higher capacity, energy. However, if we keep the layers thin and stack more of them, we increase the surface area. This allows ions and electrons to flow much faster, giving us higher power and better reaction rates. As an operator, your goal is consistency. If the coating is even a few micrometers off, it changes the battery's performance profile completely. Electrode manufacturing. We have spent a lot of time discussing the ingredients, the specific cathode and anode powders, such as NMC and graphite. Now, this slide gives you a quick overview of the recipe for putting them together. As you can see in the diagram, the process flows in three main stages. First, slurry preparation, where we mix those active materials into a liquid paste. Second, coating and drying, where that paste is spread onto metal foils. And finally, calendering, where heavy rollers press the coated foil flat. Remember the electrode thickness we just discussed in the previous slide? Calendering is the step where we precisely control that thickness to ensure the battery has the right balance of power and capacity. We won't go deeper into the machinery right now because we have entire future chapters dedicated to each one of these boxes. For now, just understand that this is how we turn those powders into the physical sheets inside the battery. Slide 1 of 2 for electrode binders. We have discussed the active powders and the metal foils, but we are missing a crucial step: how do we get them to stick together? This brings us to electrode binders. Think of the binder as the glue of the battery. As shown in the visual representation on the right, the binder's job is to adhere the active material particles and conductive additives to the current collector foil. This maintains the electrode structural integrity. Without it, the coating would crumble or flake off during manufacturing. In our facility, you will generally encounter two categories of binders. First, traditional binders such as PVDF, polyvinylidene fluoride, and PAA. Second, we have water-based binders, such as SBR, styrene butadiene copolymer. The industry is increasingly turning to water-based options like SBR because they are often more cost-effective and environmentally friendly to process compared to traditional solvents. It may seem like a minor ingredient, but this glue is what holds the entire cell chemistry together. Slide 2 of 2 for electrode binders. On this slide, we dive a bit deeper into the science of selecting the right binder. You will see a comprehensive list of characteristics on the left, terms like tensile strength, electrolyte swelling, and ionic conductivity. I am not going to lecture you on the definition of every single term in this video. Instead, I want you to understand the challenge these terms represent. The binder has a very tough job. It must be strong enough to hold the active materials to the foil, that is, adhesion. Still, it also has to survive sitting inside harsh chemical electrolytes for years without dissolving or puffing up too much. If you look at the diagram on the right, you can see how the binder acts like a web, physically connecting the active material particles and the conductive additives to the current collector. It must hold that structure together without blocking the flow of electricity. As you go through your training manual, please review the definitions of these specific properties. Understanding them will help you realize why we are so strict about material purity and handling on the production line. Electrode foils. We have talked about the active powders and the binders. Now, let's talk about the foundation they sit on, the electrode foils. In technical terms, we call these current collectors. Their job is exactly what it sounds like. They collect the electrical current generated by the chemical reaction and send it out of the battery to power your device. There is a strict pairing in our industry that you need to memorize. We use aluminum for the cathode. We use copper for the anode. If you look at the diagram on the right, you can see how these foils act as the outer bread of the sandwich, holding the active materials inside. These foils must be incredibly conductive, but they also face a physical challenge. As the list of characteristics shows, they need to provide structural integrity. We need them to be as thin and lightweight as possible to save space, but strong enough not to tear as they move through high-speed coating machines. While you might occasionally encounter specialty options like nickel foil or ED foil for specific high-performance applications, copper and aluminum are the standards you will handle every day. Separators. We have covered the anode and the cathode, the two opposing sides of the battery. Now, we need to discuss what keeps them apart, the separator. As the slide's definition states, this is a thin, porous membrane. It has a dual purpose. It must physically prevent the two electrodes from touching, which would cause a short circuit, while still allowing lithium ions to pass through freely. Think of it as a wall for electrons, but a door for ions. In manufacturing, you will typically work with materials made of polyethylene, PE, or polypropylene, PP. PE is common due to its low cost and good thermal properties. PP offers higher mechanical strength. Often, we use multi-layered materials that combine the best of both worlds. I want you to look at the diagram on the right. It illustrates the properties of separators. It is not just a simple plastic sheet. It needs a specific puncture strength to survive assembly without tearing, and precise porosity to let ions flow. Most importantly, look at the shutdown temperature bubble. This is a critical safety feature. If the battery gets too hot, the pores in the separator actually melt and close, stopping the reaction before a fire can occur. This component is small, but its impact on safety and cycle life is massive. Separators, function and importance. Let's dig a little deeper into why the separator is so critical. I want you to focus on the diagram in the center of the slide. You can clearly see the separator standing as a wall between the electrode structures. Its primary job is prevention. It physically separates the positive cathode from the negative anode to prevent a direct short circuit. However, if you look closely at the arrows in that diagram, you will see it performs a selective balancing act. It blocks the electrons, E, forcing them to travel out through the external wire to power the device, represented by the light bulb. At the same time, it is permeable to lithium ions, Li+, allowing them to swim freely through the electrolyte-soaked pores to sustain the reaction. On the bottom right, you see what this material looks like when it arrives at our factory, large rolls of thin, white film. When you handle these rolls, remember that they are also a safety device. Many modern separators feature a shutdown function. If the battery dangerously overheats, the material is designed to slightly melt and close its pores. This cuts off the flow of ions and shuts the battery down before it can enter thermal runaway. So, while it looks like a simple plastic sheet, its thickness and porosity are precision engineered to define both the cell's performance and safety. Key properties of separators. Now we move to the specific key properties that define a quality separator. On the left, you see a list of characteristics, such as chemical stability and wettability. Think about the environment inside a battery. It is chemically harsh. The separator sits soaked in electrolyte for years. If it isn't chemically stable, it will degrade, and the battery will fail. I want to re-emphasize thermal stability and shutdown. As we mentioned in the previous slide, this is a critical safety mechanism. If the cell gets dangerously hot, the separator needs to change physically, melting just enough to close its pores and stop the reaction before a fire occurs. On the right, you see a table listing specific technical requirements, such as pore sizes less than 1 micrometer and porosity ideally between 40 and 60%. You don't need to memorize every number right now, but you do need to understand that these tolerances are extremely tight. A separator that is too thick reduces energy, while one that is too thin might tear during manufacturing. Please review this table later to familiarize yourself with the specific pass/fail criteria for these materials. Electrolyte. We have discussed the solid components, the anode, cathode, and separator. Now, we need to talk about the medium that brings the whole system to life, the electrolyte. Think of the electrolyte as the bloodstream of the battery. As you can see in the text, it is typically composed of lithium salts dissolved in an organic solvent. This liquid fills the empty spaces inside the cell, soaking into the pores of the electrodes and the separator. I want you to look at the diagram on the right to understand its two main jobs. 1. Transport ions. It acts as a swimming pool for the lithium ions, Li+, allowing them to move easily between the cathode and anode during charge and discharge. 2. Block electrons. Crucially, the electrolyte does not conduct electricity. It forces the electrons, E, to travel outside the battery through the external circuit, which is what powers your device. Because this material is usually based on organic solvents, it can be flammable. This means that in the manufacturing process, how we handle and fill the electrolyte plays a massive role in the final safety and efficiency of the product. Types of electrolytes. On this slide, we categorize electrolytes into two main groups, those we use today and those we might use tomorrow. The industry standard right now is liquid electrolyte. As you can see on the left side of the diagram, this consists of lithium salts, most commonly LiPF6, dissolved in organic solvents such as ethylene carbonate. Because these solvents are liquid organic chemicals, they are effective but come with risks, they can leak, and they are flammable. This is why our safety protocols regarding fire prevention in the electrolyte filling area are so strict. On the right side of the diagram, you see the emerging technology, solid-state batteries. Here, the liquid is replaced entirely by a solid electrolyte material. This is a game changer for safety. Since there is no liquid to leak or catch fire, these batteries are incredibly safe and can potentially hold even more energy. While you will primarily be handling liquid electrolytes in our current production lines, it is important to know that solid-state technology is the next major evolution in our field. Cost breakdown of an EV battery cell. To wrap up our look at the components, let's talk about the bottom line, cost. Why do we spend so much time optimizing the cathode? If you look at the diagram on the left, the answer is obvious. The cathode alone accounts for 51% of the cell's total cost. This is primarily because of the raw materials involved. Metals like lithium, nickel, cobalt, and manganese are expensive and fluctuate in price. In comparison, the anode makes up only 12%, and the separator and electrolyte are even less. The good news is that we are getting much more efficient. As the text notes, the average cost of battery packs has dropped dramatically, from over $1,200 per kilowatt-hour, in 2010 to around $132 recently. However, with manufacturing and depreciation making up 24% of the cost, your role is vital. Every time we reduce scrap or improve the line efficiency, we are directly attacking the second biggest cost driver in the entire battery. So, while we can't control the price of nickel, we can control how efficiently we build these cells. Types of cells. We have spent this entire chapter discussing the chemistry inside the battery. Now, let's look at the packaging on the outside, what we call the form factor. Even if the chemistry is identical, the way we package the cell changes the manufacturing process completely. There are 4 main types you need to know. 1. Coin cells. You are familiar with these from watches and car keys. They are small, round, and encased in metal. While often non-rechargeable, they are crucial for small-scale electronics. 2. Cylindrical cells. Look at the bottom right. These are the classic tube shapes. They are incredibly robust and typically feature a resealable vent to release gas pressure safely. You will see these used everywhere, from power tools to Tesla vehicles. 3. Prismatic cells. These are the rectangular metal cans shown in the middle. Because they are flat, they stack together very efficiently, like books on a shelf, making them excellent for large EV battery packs. However, a key challenge with these is their tendency to swell over time. 4. Pouch cells. Finally, look at the flat, silver packets. Unlike the others, these have no hard metal case, just a flexible foil. This makes them very lightweight and space efficient, but for you as operators, they require the most care. They are soft and susceptible to physical damage, so a sharp object or rough handling can easily puncture them. Understanding the form factor is the first step in knowing how to handle the product safely on the line. Comparing types of cells. Now that you know what these cells look like, let's compare them side by side to understand why a manufacturer might choose one over the other. This table summarizes the benefits and challenges of each form factor. First, let's look at the coin cell. While it is perfect for small devices like hearing aids due to its compact design, it has low energy density and low power output. You won't be building electric cars with these. The real battle in high-power applications, such as EVs and power tools, is between the cylindrical, prismatic, and pouch cells. Cylindrical cells are the veterans of the industry. They are highly robust and have standardized sizes, like the 18,650 or 21,700 formats you see in many battery packs. They are reliable and safe, which is why they are widely used in EVs. Prismatic cells offer a sturdy mechanical build like cylindrical cells, but in a slim, rectangular profile. This makes them easier to stack. However, a major manufacturing challenge here is the potential for swelling over time, which we must account for in the pack design. Pouch cells are the most unique. They offer the highest energy density and are very lightweight because they lack that heavy metal outer can. But remember what I said earlier, this makes them vulnerable. They require extra protection because they are easily damaged and, like prismatic cells, face risks of swelling. As you review this chart, think about the challenges column. These challenges, like swelling or the need for protection, are exactly what our manufacturing quality controls are designed to manage. Battery manufacturing factories in the United States. To conclude Chapter 3, I want to zoom out from the microscopic world of lithium ions to the massive scale of our industry today. The images you see here represent the new reality of manufacturing in the United States. We are not just building factories, we are building gigafactories. Top left, this is the Blue Oval SK site in Kentucky. To give you an idea of the scale, this single facility is roughly the size of 60 football fields. Top right, you likely recognize the Tesla Gigafactory in Nevada, which pioneered this large-scale approach. Bottom left and right, we see facilities from Ultium Cells, a GM partner, and LG Energy Solution. These massive plants are popping up across the country, from Michigan to Kentucky, Tennessee, Georgia, and Nevada, forming what many call the battery belt. They are designed to deliver large capacities, measured in gigawatt-hours, GWh, to support the millions of electric vehicles hitting the roads. I show you this to emphasize one thing: opportunity. You are joining an industry that is growing exponentially. The skills you are learning in this course, understanding cathodes, anodes, and cell structures, are the keys to operating these massive facilities. Thank you for your attention in Chapter 3. In our next session, we will move from the cell's structure to the equipment used to build it. And that brings us to the end of Chapter 3. We have covered a lot of ground today, from the atomic level of cathodes and anodes to the massive scale of the gigafactories. You now have the foundational knowledge of what a battery is made of. In our next chapter, we will turn our attention to the how, diving into the specific machinery and processes used to turn these raw materials into finished cells. Thank you for your time and attention. I will see you in the next session. Thank you. We'll meet again in the next lecture.